In this video we're going to look at the Hess cycle, where you are given the enthalpy of combustion data and you use that to calculate the enthalpy change for another reaction. So the example we've got here is we've got 5 carbon atoms, 6 hydrogen molecules going to make a molecule of pentane. This is the enthalpy of formation because we're making 1 mole of a product, 1 mole of a substance from its constituent elements, and everything being in its standard state. Now the trouble with this reaction is, if you try and mix carbon and hydrogen together, you're not just going to get pentane, you're going to get butane, ethane, hexane, all sorts of alkanes being formed. So we have to calculate the enthalpy change of formation via another route. Okay, and what we're going to do is we're going to look at the combustion products. Now, because a chemical reaction, the number of atoms on the left hand side must equal the number of atoms on the right hand side, it follows that when you combust carbon and hydrogen to make carbon dioxide and water, or you combust pentane, which contains carbon and hydrogen, you will also make carbon dioxide and water. So what we have here is we have a common starting point and a common finishing point here. So how does this look on a Hess cycle? Well, the Hess cycle was showing that with this red arrow here, the combustion products of those elements themselves. Now that's our starting point here. The combustion products is our finishing point. Hess's law states that regardless of the route taken, the enthalpy change will be the same. So this means that the overall enthalpy change for the combustion of the reactants will be the same as the enthalpy of formation of pentane and the enthalpy of combustion of pentane. Or in other words, the red arrow equals the purple arrow, and the purple arrow is made up of these two components. The red arrow is made up of the enthalpy of combustion of the the enthalpy of combustion of the reactants. Now we are actually interested in the enthalpy of formation in this reaction, so so we need to rearrange our equation, and we do that by subtracting the enthalpy of combustion of the products from both sides. So we now get the enthalpy of formation, and I've just generalized this to be the enthalpy change here, is equal to the sum of the enthalpy change of the reactants of combustion data minus the enthalpy of combustion of the products. And this is regardless of the reaction that you have. The combustion products will be the same from both the reactants and the products, so therefore you can use this. A handy way of remembering this is that the enthalpy change when using combustion data, so C for combustion, is the reactants minus the products. And if you could think of a way to memorize that, well, so be it. Okay, let's have a quick look at an example on the next page. So here we've got carbon plus 2 molecules of hydrogen to make methane. The enthalpy of combustion data shows us that the combustion of carbon is exothermic to 393 kilojoules per mole. Combustion of hydrogen is exothermic to 286 kilojoules per mole, and methane exothermic to 890 kilojoules per mole. So we said that the enthalpy change for this reaction is the reactants minus the products. So the enthalpy change of the reactants of the combustion of the reactants is 1 carbon plus 2 moles of hydrogen. So that's 2 times minus 286. That gives us a grand total of minus 965. We're going to subtract away from that the combustion of our products, and that gives us this equation here. You need to show these values, as also noting that you need to show this formula as well. So the first step in your calculation should be using this formula. Therefore, the enthalpy change of formation is for this reaction is minus 75 kilojoules per mole. So either using this formula or actually using the Hess cycle will get you to the same points. Okay, so thank you for watching this short video.